One. Hi, welcome back to Math 234 on a special spooky version of triple integrals. Today we've got the second half of 15.7, so we're just going to continue on with doing our triple integrals in rectangular coordinates. Why am I specifying rectangular coordinates? Well, that's the spooky part. But we're saving it for the next lecture, so you can look forward to that. Not a ton of warm up to do really. It's just kind of we dive right into some examples. So let's go do that. So let me find my water bottle. Okay. So we want the volume of the region bounded in the back by x equals 0, in the front and the sides by the cylinder, x equals 1 minus y squared, and on the top of the paraboloid, z equals x squared plus y squared. And we conveniently have some pictures already sketched for us. So let's rely on those to get an idea of what the heck it is we're looking at. So we are sort of bounded by that L bracket in the back, right? Maybe it's easiest to look at this first picture before we add in the cylinder, just to get an idea of what our shape is. We've got, again, that parabolic cylinder kind of gliding right up the z-axis. It's moved out to x equals 1, or I guess maybe the point 1, 0, and then whatever z wants to be. All right, so we've got that axis going up to the vertices of all those parabolas. And again, it's running parallel to the z-axis. It's just shifted out by 1. And we're then going to add a paraboloid into that, which gives us that red shape over there to the right. But again, we can kind of look to see that this thing definitely has a back and a bottom that make a lot of sense. Sort of that front blue shape is going to be relatively easy to see, but it's that intersection between the paraboloid and the parabolic cylinder that ends up being a little odd to visualize. But effectively, we've got this, sort of parabolic shape in the middle, and then it goes concave, like it dips into itself to come down to the origin. So there's that red shape kind of going through the back of that paraboloid that we can see right up front. So maybe more imagine this thing as like a bowl that's been cut in half. And then we're going to go outside the bowl for the space that we're looking at. We don't want space that's inside the bowl, instead the space that's under it. Maybe it kind of looks like half of a coffee filter, depending on the kind of coffee machine you use. Kind of looks like my coffee filter. That's not exactly helpful to you. Maybe I should have brought my coffee filter into class. Well, things you think of at the last minute. So our first goal when trying to figure out the volume of this thing, we know that we're going to want to do it with the triple integral. We're in the triple integral section of the notes, so that's kind of a giveaway. But we want to integrate this thing 3 times to come up with our volume. We just need to figure out what order we should do it in. So let's just run down the line and see which of our options makes sense. So let's just start with dx. Ooh, hey, so let's just start with dx. That means we need to come from the back in. Right, so we'll be coming along like these lines. And then we'll be coming out the front like that. And we wanted to decide if it's a good idea to start with x. Basically, I'm just looking for, do I have a clear back and a clear front if I try to do dx first? And I think that my front makes a lot of sense. Right, my front is for sure going to be that blue paraboloid, right, coming out of right here, where that purple thing, that purple line is. Everywhere on the front, I have that blue paraboloid. So I have a clear exit if I'm coming from the back. But it's the back where I think I run into problems, right? Depending on where I am. If I'm coming in near the sides, hey, I said I'm coming in near the sides. Stop it. One more time. If I'm coming in near the sides, I hit that plane where x equals 0, right? That gray back that we had from the start. But if I come into the shape near the middle, I run into that red bowl shape in the back. So approaching from the back of this shape, I hit the solid on two different surfaces, which isn't ideal. Doesn't mean we can't do it, but it does mean we would have to split up our domain into two separate solids where we'd be integrating dx first. Basically, there'd be the portion where the plane is in the back, and then there'd be the portion where the paraboloid is in the back. I think I said paraboloid earlier when I meant parabolic cylinder, but well. There's a shape where the plane is in the back, the gray plane, and then there's a space where the red paraboloid is in the back. Let's use colors because they're available to us. So again, not super ideal. So we don't really want to do that. So I'm just going to get rid of the purple lines because they weren't helpful. That's not the way that we want to try this. Or at least we're going to keep looking for a better way. And since this is the first example in a math class, there's going to be a better way. So let's try y next. Y means we come from the left and go to the right. And again, we're looking for the same sort of ideal case where as I move from left to right, I have a clear outer surface and a clear left surface and a clear right surface. And at first glance, maybe we do have that because I think on both the left and the right, when I come from the left, the first surface I'm going to hit is that blue cylinder. And when I exit out the right, the last surface I hit is again the blue cylinder. So at first glance, maybe that looks okay, but you might be noticing a bit of a problem. In particular, as we pass through the middle, we're going to hit a bunch of blank space, right? Because we're going to go into, we'll go into the blue surface or the blue cylinder. But then we're going to pass through the red paraboloid. And then we'll pass back into the red paraboloid and then out the other end. So we're passing through a few different surfaces if we go y first. So again, I don't think that's a great plan. So let's nix doing y first and go try dz. Since that's the third option, since none of the others have worked yet, hopefully this one will. dz means we're going up. So something like that, and then we'll come out up here. Right, that's our dream, is since the other two orders didn't look very nice, that dz will work out nice for us, and indeed it does. If I'm going from bottom to top, I have a very clear bottom surface, which is my plane, the gray plane z equals 0, the one that's on the bottom. And everywhere on this solid, the top surface is that red paraboloid. Right? It is the top everywhere in the solid that we've made, including its intersection with the cylinder, which is at the very, very tippy top. But that blue and red paraboloid at the top will be shared by both surfaces. So we can still consider our red surface to be on top the whole way through. So dz is first. That's what we just decided. So now we've got to go figure out what we're gonna do second. Which might mean that it's helpful to draw our remaining shape. So what we want to do with what's left is project down into the XY plane. That's not super clear what I'm projecting there. Maybe black? Maybe gray. Nope, gray doesn't show up at all. How about the blue one? Cool, that'll do. So project our shape down into the XY plane, and then start looking at the next bounds. So oop, draw some axes in here. And what shape do we have left down there? This is parabolic. So let's see if I can do my best to draw a paraboloid. Okay, I'm gonna give it one more shot. So that was really bad looking paraboloid. Yeah, slightly better. Okay, come on, just like pick one and settle. Slide it out. Okay, we're gonna call that good enough. So this was that projection down into the XY plane. Y is here. Oop, wait a minute. Why'd I put Y over there? I don't know. That's clearly X. And this is Y. Not too often I get the letters wrong. That's at 1, that's at 1, that's at -1. Right? If I'm just looking at the paraboloid, which I know that this thing is going to have the equation. Nope. X equals 1 minus y squared. I can look back at my original couple of equations to see where I've got that blue and that red equation from. But so I've got that paraboloid, x equals 1 minus y squared. It's not a paraboloid anymore. It's just a parabola. And we want to integrate over that region. And we'd have our options of what to integrate with next. We'd either do y or x second. Right? Either one will work. If I'm going to do y first, I have to solve that blue line for y, which would mean, come back here, I'd have y equals the square root of, what is that, 1 minus x? And y equals the negative square root of 1 minus x. I do at least still have a clear top and bottom with the positive square root and the negative square root. So I could integrate it that way. But I don't know. Those bounds don't look nearly as nice as 1 minus y squared. Because I do still have a clear left and right boundary as well, being 1 minus y squared on the right and just the y-axis on the left. That y-axis, of course, being x equals 0. So why don't we try that? Why don't we try doing x second? Just because I think the bounds look a little bit nicer. So we'll do up here, circle this equation, dx second. All right, so hopefully you agree with the order I picked. Because now we just have to go and actually do that triple integral. So I need the triple integral of just dv over our solid, because that's what the volume will be equal to. And that's going to look like the triple integral of, we decided on dz, and then dx, and then dy. And we'll do z first. So I'll mark off a little bit of color there. And looking at z, the thing that we decided was that if we were going from bottom to top, we would first hit the plane z equals 0, and we would then hit the red surface z equals x squared plus y squared. Then when we did x second, right, our left boundary was x equals 0, just the y-axis, and our right boundary was the blue paraboloid, 1 minus y squared. And what's our last step? We need bounds for y, which if I just go take a look at them, a bottom and a top, I'm going from -1 up to +1. I just need the intersection of that blue paraboloid with the y-axis. Right, and with all that said, let's just get to integrating, because this is going to be kind of fun. So I now have an integral of, well, a double integral. I'm doing the z integral first. dz integrates to z, and then I have x squared plus y squared minus 0. X squared plus y squared, then minus 0. dx dy. I'm going quick in class, so some of these are going to come out kind of ugly looking. This is still from 0 to 1 minus y squared. And then we'll still go from -1 to 1. So now I get to do the x integral, which that thing is going to integrate to 1/3 of 1 minus y squared, that thing cubed, plus y squared times 1 minus y squared dy. We're going to integrate from -1 to 1. Now I have to integrate that. So it can't be that bad. So let's just, I don't know, try to work our way through it. Oh, I am already running out of space. That's not too surprising on this one. So before I integrate that thing, I don't know, I might check to see if I have some sort of a u substitution, because trying to multiply that all out looks like a chore. So I try 1 minus y squared being equal to u, which means my du would be just -2y. 1 minus y squared, meaning du is -2y dy. Maybe mark that off in blue, because that's kind of the point I'm thinking of. But I don't really see a du showing up anywhere. None of my y's are linear. They're all at least quadratic, if not some higher power. So I probably just have to multiply it all out. Maybe it won't be as bad as it looks. So let's just get to that. If I go to Pascal's triangle, and I'm looking to FOIL out a cubic, or rather multiply out a cubic. That line in Pascal's triangle is 1, 3, 3, 1. So those will be the coefficients of 1 minus y squared cubed, right? If I FOIL out a binomial, if I cube out a binomial, there we go. It's not foiling when it's not just two of them. My coefficients will be 1, 3, 3, 1 as I move my powers from the left side to the right side. Also, I'm going to multiply the whole thing by 1/3. So this will be 1/3, 1, 1, 1/3. And since one of those is negative, every other entry is going to also be negative. So to get that thing cubed out, it is 1/3 times 1 minus y squared plus y to the 4th minus 1/3 y to the 6th power. Handy way of just multiplying that out. Otherwise, you could FOIL once and then distribute a second time, you'd get to the same thing. But to distribute out the other half, this is a plus y squared and a minus y to the 4th. Slap a dy on the end. Don't forget we're going from -1 to 1. And let's start simplifying because it actually works out kind of nice. I have a minus y squared and a plus y squared. I have a plus y to the fourth and a minus y to the fourth. So I only get two terms that survive. 1/3 and negative 1/3 y to the sixth power. And by the power of technology, I can shrink this a little bit to give myself space for one last line. Integrating 1/3 minus 1/3 y to the sixth from -1 to 1. So 1/3 integrates to y, evaluated from -1 to 1 will be 2/3. Minus, let's see, y to the sixth will integrate to y to the seventh over 7. Plug in 1 and -1 to and take the difference to get 2. So 2 over 27. 27. 21. There we go. Pretty sure 3 times 7 is indeed 21 and not 27. Cool. So 2/3 minus 2/21. Yeehaw. I mean, yar. Should stick to the genre appropriate colloquialisms. All right. Let's try the next one. And let's not spoil too much of it. So, what do we want next? Consider this already given triple integral. Ta-da! Looks like z is from 0 to, well, let's read it inside out. Oh yeah, z is from 0 to y squared, y is from -1 to 0, and x is from 0 to 1. And our goal is to rewrite that integral in terms of all 6 possible combinations of dz, dy, and dx. Are those all 6 permutations? Yeah, all 6 permutations of dz, dy, and dx. Cool. So let's give that thing a shot. Before we try to rewrite it, I think that we need to have a graph of what we are looking at. So we'll draw ourselves a coordinate space. So maybe something about like this. I think will give us a decent enough shot. Cool. So z, that axis, x, that axis, y, then is this one. But I might notice right away that y is supposed to go from -1 to 0, while the other ones get to stay positive. So I need to extend that axis backwards. All right. And then I'll start trying to put a graph on this space. So first one I want to look at. This is z equals y squared. All right, so I'm doing z first. I know that that should be my first equation. And rather than trying to jump straight into a 3-dimensional diagram, I just want to plot it sort of in its 2D spot first. So that parabola should open in the z direction, and I want to draw it in the zy plane. So maybe something like this shape. Maybe let's try and gradual moving up there in the back. Cool. Let's go with that for now. So that's the parabola I draw in. I also have the plane z equals 0. So maybe I could just shade that in down here. Hopefully that doesn't get too busy. because then also. And yeah, we'll again get rid of those lines if it makes the diagram too difficult to read. But for now, that's kind of the Z part that I know we're going to be looking at. I'll need to extend that parabola in a minute to make it a 3D shape. But for now, I'll leave it just right here. Because now I want to go look at the Y boundaries. And the Y boundaries are X or nope, Y boundaries should start with a Y. So really just interested in getting the X today. Y is the middle part. So it's going to be bounded by Y equals 0 and Y equals -1. I could think of those as planes, or I can just think of them as lines in the other two planes that include Y in them to get a sense of where we should be looking. So Y equals 0 will show up as both the X axis and the Z axis. Those parts are already drawn in. But if I go to look at Y equals -1 in the other two planes, I think I might have been saying Y equals 1 when I meant Y equals -1. Sorry if that was the case. Y equals -1 should be that line right over there. And this line, oops, that was a really terrible looking line. This line right here, hopefully that's parallel to, hopefully that's parallel to my X axis here. If I look on this screen, I can see it a little bit better. All right. Hopefully we did an all right job making that thing parallel. So that's our plane, Y equals 1. And I think I can start filling that part in. So let's just go do that. Maybe about like here-ish. And then over. Again, hoping that I hit these things so that they're parallel. And then I can just erase the part that I didn't need. Cool. So I think that is going to be the back of my shape. Ah, stop it. I've got that plane in the back. Z equals Y squared is going to be a cylinder. It expands along the X axis. So I also get this sort of sloping shape on the edge of that plane. To create this shape altogether. Then let me arrange that. Bring it forward. Yeah. All right, so I think I've kind of got a shape that's showing up here. I also should shade in probably this back part. Last thing I need to do is figure out where that thing should have stopped. Because the dx integral tells me that part. I know that here in the back, I've got Y equals -1. I know that along this green line, I had Z equals Y squared. I really should apply to both, so I'll move it up a little bit. So I need my limits for X, but I can just look at that very last integral and see that they go from 0 to 1. Which means if I look at that point right there, it's got to be an X value of 1. So maybe I'll fill this guy in with one last little splash of color. Call you X equals 1. And I'm bounded in the back by X equals 0. So that's, I think, my shape. I think those lines ended up being sort of superfluous, kind of hindered the diagram a little bit. So let me erase those, redraw them in kind of about like that. And then if I dare try to shade in my top surface. Yeah. Hopefully that paraboloid's starting to take some shape. Or paraboloid. I don't think it's a paraboloid anymore. Keep saying that. This one's definitely a cylinder. But then this is the thing that we want to change our integral to. We want to go in a few different orders based on this diagram. So what are we going to need? Actually, I think at this point, we're probably about ready to look at the next half down. So I took the liberty of just kind of filling in the bare bones part for each of the 5 remaining integral orders that we need to do. I organized them based on what we're going to start with. So starting with dz, starting with dy, or starting with dx. And then we'll fill out the bounds from there. So with that said, getting into our first change, which is where we're going to keep the same starting integral, keep dz first, and then try and look at the other two. So if I look at my bottom and my top shape, they are the plane, z equals 0, and the parabola, z equals y squared. Notice that these will not have changed from the integral that we started with. But since I want to be thinking about how I actually come up with these shapes, right? I want to be going from top to bottom. So I want to be coming from the bottom where I'll first hit that plane, z equals 0, and then I will hit the parabola, or the parabolic cylinder, z equals y squared. Maybe that is a slightly easier to read diagram. So I start by hitting the gray shape and then the green shape. After that, I want to go do dx second. And a couple of thoughts. One is I could just continue looking at this 3D graph in order to come up with my secondary bounds. I think it's not too bad on this one. I think we could probably see we're going to go from the back at x equals 0 to the front at x equals 1. And then y goes from -1 to 0. -1 being the blue shape, 0 being the x-axis. But it might also be a little easier to make a 2D sketch. Of the region that we have. So if I go back, calling this thing x, that thing y, and start filling in the remaining shape, well, I've got my blue line down here at y equals -1. I've got the purple line at x equals +1. And this is my region of integration. Keep in mind that we'll be staring down the barrel of the z-axis here, right? We've sort of rotated our graph or rotated our space. So we're staring directly down the z-axis and looking at its projection down into the xy plane. Because that parabola, the parabolic cylinder, has the same projection down here. It projects also over top of this square. X equals 1, y equals -1. So this image, the projection down into a plane, ends up being just a rectangle. So the order between x and y won't end up mattering. except that we have to put it in a specific order because that's the problem wanted. But yeah, so I think that's the first couple of orders. So for the next one, we're going to look at y first. So if we want to look at y first, what do we want? Well, to get the first set of bounds, I'm going to need to look at the 3D shape again. So I want to come from the left to the right. Granted, my shape is a little bit twisted, so left and right are not exactly left and right, but there's still a left side and a right side. Right? If I come barreling down that y-axis, the first surface I'm going to run into is the blue one, that blue plane. So my initial bounds for y should be -1. But then for my upper bound, my right bound, the second surface I run into as I'm traveling traveling in a direction parallel to the y-axis, my exit surface is the green one. But that green one is currently in a z equals a function of y format, so I need to change it around so that I have y equals the square root of z, and y equals the negative square root of z. Right, since when I take the square root of a variable, I'm going to end up needing a plus or minus. So if I want to write this thing as a function of y, I'll need both a positive and a negative square root. And because we're going to be exiting out the left half of the coordinate space, right? The parabolic cylinder I'm interested in is over there on the left of the x-axis, or the xy plane, xz plane, excuse me. Right, it's on the left half of that y-axis. So my upper limit should be the negative square root of z. And then I'll want to come up with bounds for the next two orders as well. Again, probably could read those from the 3D shape, which if you can get that, great, awesome. But in case reading from that 3D shape gets a little confusing, let's go draw another 2D diagram. So if I draw in another shape, this time I want to be staring down the y-axis. And also I'm going to be flipping this thing around, so I'm looking at it from the back. That way I get x over here and z up here. All right, so I'm looking at this thing from behind. So I'm rotating it to look around the backside so that the first shape I see is the blue sphere or the blue plane. Hey, stop that. Fine, 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 fine. I'll make you smaller from the bottom. Happy now? Cool. Well, so that's the first shape I'm going to see. Fill in those bits. Where I could look down maybe this spot right here and see that purple line where x is equal to 1. Oh no. Hang on 1 second, technical difficulties. Pen ran out of ink. But again, I'd see that purple line there, and the parabolic cylinder is behind us, or maybe out in front of us. It's behind this blue shape. So it'll be coming down like that. If I draw in those same lines I had going earlier. So I've also got this top line up here at z is equal to 1. So again, I ended up with another rectangle that I'm integrating over. And it's just 0 to 1 for both x and for z. So if I'm doing x first, this is 0 to 1. And z is also from 0 to 1. Which means that things don't actually change when I flop the order of dz and dx. Because they both went from 0 to 1. But maybe it'll be more interesting if we add some color and track what's happening here. I was giving x purple, so it's going from 0 to 1 with a purple mark. And we'll look at z going from 0 to 1 in green. Notice again that it didn't matter what the second two orderings were. If I'm doing dy first, I've got the same bounds of -1 to negative root z both times. Hi. Yeah, we are looking through the back of that square. I agree that that square is at y equals -1. But we're projecting into the xz plane. Right? So yeah. So this is all now, yeah, we're trying to take y out of the equation so we can get x and z. Yeah, again, I do agree that that thing is at y equals -1, but that's why we have, yeah, this lower bound is at -1. Yeah, so I knew I was going to go slow at this. All right, for my last trick of this problem, at least. Yep. We want to do x first now. And if I'm looking at the x's, this one's pretty straightforward. It's bounded in the back by the plane x equals 0 and bounded in the front by the plane x equals 1. Right? Not a lot happening in the x dimension on this solid shape. So if I just go fill that stuff in, we're from 0 to 1 in the x dimension. So same thing when we try to do it the second time, 0 to 1. So now we just need to get our y and our z bounds. And again, you may find it helpful to draw in an additional 2D diagram. Slide that down a bit. And what are we looking at this time? We're looking down the x-axis. So let me just mark that right here. We have a y-axis running left and right and z-axis running up and down. And if we approach that shape from the left side, I think we will see the parabola z equals y squared and the plane y equals -1. Roughly about here and about here. With that part shaded in. So this was z equals y squared or y equals negative root z. And over here, y equals -1. So I think we'll use those bounds to figure out y and z. So if I'm going to do y first, it's going from -1 over to negative square root z. And then z just goes from 0 to 1. Just top or bottom to top is 0 to 1. And if I've got to do it in the other order first, I'm doing z first instead of y. Its lower bound is 0 with its upper bound being y squared. And then y goes from -1 to 0. Cool. So to try to put all those on screen at once, here they are. Now, I know that this is one of the trickiest problems, just because changing these orders is the kind of the hardest part of this section. I think once you actually get to the integration, I mean, it can be tedious, but it's not so bad. You can also obviously just like go use, well, at least when you're working on the homework, you can go use something like Wolfram Alpha to help you compute some of the nastier integrals, or at least check your work. But for some additional practice, I included another problem over here of trying to sketch out what they all look like. And I do think that changing this order is a particularly important skill. Hint, hint. So might be worth looking at this example sometime. So over in the margins of my notes, just head over to the right side of the example we just did. And here's the shape that I've drawn up. I also included a actually computer generated diagram. So you don't have to entirely rely on my sketch. But I got that shape over there on the right. And then also kind of tried to show what a projection looks like. Anyway, I think that can be worth checking out sometime. All right, how are we doing on time? Oh, yeah, yikes. Okay, well, I think I'll have just enough time to set up both of the next two problems, and then maybe I can work them out in a couple of minutes after class. Okay, so on example 7.3, you want to express the volume of the wedge cut from the cylinder. X squared plus y squared equals 1, conveniently already drawn for us. By the planes z equals -y and z equals 0 in two different ways. So let's go take a look at those two planes and try and sketch them in. Since I already have my cylinder drawn, I'll just add in the detail for the next two planes. Z equals 0, just the xy plane, is going to be just this part down here. Let me actually try that one more time. Do without whatever that rattling is, but whatever. Okay, so I've got that plane down at the bottom right there. I also know that z equals y, or z equals -y, will intersect my shape along this x-axis. Right, if z and y are both 0, I get that line right there. And then I've also got z equals -y. Hey, stop that. Z equals -y is going to look kind of something like that right there, sort of. If I keep extending the plane just to look like the plane, I think it should be something kind of like this. Hopefully all these lines are parallel to each other. So that's what I'm aiming for. So if that green shape is the plane, it looks like it'll intersect. Or rather, it'll cut this wedge out. Right here. So that's the thing that I'll look to integrate. And if I set up my integral, it looks again like doing z first is going to be easiest. So I'll just fill that in. We're going to go from z equals 0 to z equals -y. And then I've got two options for sketching out the blue shape on the bottom. I could either do, it's actually pretty similar to the very first problem we did. I could either do a top square root and a bottom square root, or I could do a left square root and a right square root. We know we're going to do dz first. I think up next, I would look at doing negative. This is going to be a little bit rough to write in. Negative square root of 1 minus x squared up to y equals 0. And do dy second. And then finally, I'll do x, which will go from -1 to 1. Going from the back to the front. And I could rewrite that another way, but in the interest of time, I'm gonna, oh boy, be totally out of time. So one last thing that I need to write down is the average equation for three-dimensional shapes. So if I look for the average temperature of something over a 3D shape, it is probably what you'd expect. Because we've already seen average calculations a few times. Blah, 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 blah. T of x, y, z, dv. So if I want the average of some function, I should just take its triple integral over the domain and then divide by the volume of that domain. And then I would set up, I mean, this thing has a nice rectangular, very nice rectangular shape. So the integral comes out very nice. But the average value equation is the one that we needed. Cool. All right. So I am over on time again. Surprise, surprise. So if you've got somewhere else you need to be, go have a happy Halloween. I will see you again on Monday. But since I've got some time, I can stick around and finish these two problems. So I'll take a couple of questions first, if there are any. So, okay. Zoom. Calm down, buddy. All right. So if I actually wanted to, let's start with the one that we were just working on. Just because I know it'll be nice and easy. If I want to calculate this average value, this looks like 1 over the volume of a box bounded in the first octant, so zeros for x, y, and z. And its dimensions are going to be 3 by 1 by 2. Try to draw in a better 3 right there. And then I can just integrate this function in whatever order I like because it's all rectangular. So 0, 0, 0, 2. Let's just go in order. 3, 1, 2. X plus y minus z d z d y dx. And then just integrate right down the line. This will be 1 over 6. So that's what the volume will simplify to. Integrating that part in the middle. X. Well, it'll be zx from 0 to 2 is 2x. Zy from 0 to 2 is 2y. And minus z squared over 2 from 0 to 2. 4 over 2 simplifies to 2. dy dx. Still 0 to 1, still 0 to 3. And then I can do a dy integral. So this will be still that 1 over 6. 2xy from 0 to 1 will be just 2x plus 2y squared over 2. This is just y squared. From 0 to 1 is 1. And 2 integral, or 2y from 0 to 1 is just 2 again. dx, we're still going from 0 to 3. So to do this thing one last time, 2x squared over 2. So just x squared. From 0 to 3 is 9. Plus 1 minus 2 is just minus 1. So integrate that, or integrate -1 dx from 0 to 3. I'll get just 3. So I get 1/6 times 6, which is 1. Ta-da! Thanks. And I'll come back up and finish 7.3. If I wanted to write this thing out another way, maybe I'll just use technology to copy and paste it. Yeah. But swapping out my bounds so that I do X first and Y second. So I think that's probably going to be the best way to go about this thing. Yeah, I think trying to do a different variable first would get a little tricky. So I don't want to do it that way. Doing dx first. So if I go from back to front, I'll have the negative square root of 1 minus y squared to the positive square root of 1 minus y squared. And then y just goes from -1 to 0. And I get my choice of which one I want to do first, or which one of these I want to do at all. And I think the one on the left looks a little easier. So I suppose you might ask, why do I think the one on the left looks easier? It's a totally valid question. On the one hand, I don't have two different square root bounds to deal with. I usually think that that's nice. One of my intermediate bounds, so one of the ones in the middle is 0, also tends to make integration nicer. Also, I looked ahead and saw that my first integral is going to give me -y dy dx, where again, I'll go from the negative square root of 1 minus x squared to 0, -1 to 1 for x. And I can see after integrating, I'm going to have a -y squared, which means that I won't even have to deal with the square root by the time I get to my third integral. 1/2 from -1 to 1. I'm going to have a double negative here. So this just becomes 1 minus x squared. Once again, it'll get squared away, which I think is particularly kind. And then I have to integrate this thing. And what are we going to get? This looks like 1/2 times 2 minus 2/3. Since x squared integrates to x cubed over 3. And I don't know, in the end, is that just 2/3? I think it is. 1 minus 1/3 is 2/3 if I just distribute the 1/2 through. And finally, since you guys stuck around, I have two last bonus problems that we're not really doing, but just some hints that I want to give on a couple of tricky web work problems. One is this one, problem number 4. I find the sketch sometimes is a little hard to visualize because even though it includes the origin's not an interior point of this. Is this a prism or a pyramid or something? A tetrahedron. There we go. And the word was right there the whole time. This tetrahedron kind of has this shape. And so it's helpful if you can visualize this when you're doing that problem. So if you get to problem 4, it might be worth coming back to check this diagram against your own. Make sure that your idea fits. And problem 8 is actually the same first problem that we did, except we're, of course, going to add b's to the problem again. So we're putting b's inside that shape that we calculated the volume of in problem number 1. So I thought it was relevant So I sketched it here. Also, a freehand sketch of coming up with that shape at the beginning. That's got a few more labels on it. Maybe that's makes it more helpful to see what's going on. Cool. All right. That's it for me, for real. Y'all can get out of here. Thanks for sticking around. I appreciate it. Have a happy Halloween, and I'll see you on Monday. Okay. Bye, 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 bye. And then, as was pointed out just after class, I made a mistake on one of these bounds. This lower bound, when doing the dz dy dx integral, should have been the negative square root of 1 minus x squared. Since we are doing the left half, ooh, that was a terrible line. We're doing the left half. This shape. And since we've got another question, do we lose the next? Gotcha. Yes, I do know exactly where you're going to be going with this one, because this part I did get right magically, even though I got a bunch of the other stuff written down wrong. Guess I just kind of foresaw the answer. So I've got a double negative by the time I get to the step in the middle of the screen. So I've got the negative on the y. Ooh, wait, do I?
Doesn't get negative y squared. And then you square the
Yep. You're right. The negative on the square root doesn't matter in the end. So it is going to be negative y squared over 2, but then I'm going to get 0 minus square root squared. So if I were to just fill in some extra detail right here, large you over there. Again, this thing is going to integrate to y squared over 2. So I'll add in that detail. This is going to be then negative 0 minus negative this guy.
Yeah.
Yeah, because it'll be, plugging in the, plugging in 0 for y. Yeah, there we go. Plugging in 0 for y makes it 0. For a hot second, I thought I'd plug in 0 for x. I'm like, oh no, I screwed it all up. But no, this is fine. But yeah, it is the double negative right there that becomes positive. We can also double check that against the answer we end up getting. We know we're trying to calculate volume. And if we ended up with a negative volume, that would have been bad. Yeah, volume should come out positive. So yeah, we got our positive 2/3, which means that it was probably right. Yeah, for sure. You are welcome. And now I'm for real done with this video. Okay, bye, 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 bye.